Marcone Pereira from Universidade de São Paulo. He will talk about reaction diffusion problems with concentrating oscillate terms on the boundary.
Okay, thank you by the presentation and the organizer by the opportunity. I'm very glad to be here talking IMPA, my first time here. Very nice for me. So I will talk about a problem, a reaction diffusion problem, and it's a toy model, okay? We are considering a parabolic equation. Let me show the equation, it's better. It's like a toy model. We have a parabolic equation, and we are supposing that the reaction term concentrating near the boundary, okay? And we have a potential term concentrated at the border too. So, let me, the equation is posed in the fixed domain omega. So, and we have a neighborhood of the border that we call omega epsilon, depend on a parameter epsilon, and this parameter model the concentration at the border in the sense that this strip, it's shrink to the border, okay? And when epsilon goes to 0, we are allowing oscillating behavior to the same order of the narrow of the strip, okay? So, and we consider the characteristic function of this neighborhood, omega epsilon, and we put a 1 over epsilon term in front of it to model the concentration, okay? So we can think it's a kind of problem like species just reacting near a border of the lake, some kind of, this kind of phenomenon, okay? And of course, I'm just talking about a scalar case, but we can consider a system here, and the system should be or must be a semi-linear system, but with the property of to be gradient too. Okay, it's just this. Okay, and we have to work in R2. In high dimension, we have to be more careful. So let me talk. Here I'm defining the open set, the neighborhood, the narrow strip, and it's given by, we have to use the normal, outward normal vector of the boundary, okay? The thickness of the neighborhood is given by this epsilon term here in front of this function g epsilon, and this function g epsilon model the oscillation by this expression here, okay? So the g epsilon function is defined up with a function g with 2 variables, and this function is positive, smooth, and it's Lx periodic in the second variable here, where we put the 1 over epsilon term. So when epsilon goes to 0, this function will oscillating, you produce this behavior that I like that, like here, no? Okay? So, yes. And since we are interested in what happened with the solutions when epsilon goes to 0 here, we'd like to understand how the dynamics, the behavior of the dynamics, like the behavior of the attractors of this problem. So we will consider some functions, nonlinearities, condition, dissipative and growth condition to exist the attractor for the limit problem that I will show. Another hypothesis that you have to suppose here, it's about the potential terms, okay? We need the uniform bound of them, okay? and we need to the existence of the limit, the weak limit of the functional. So it's clear that when epsilon goes to 0, that the problem will converge to a problem with a nonlinear boundary condition, okay? It's pretty, it's almost obvious. What is interesting here that appear a boundary coefficient here, a function mi, that is given by the average of the function g, okay? So it's a kind of term that appear in homogenization problems, okay? So it's like an average of the function g. And it shows that the oscillating behavior can that the limit problem can capture this oscillation through this term here in the nonlinear part and the potential part too. Okay. So if you see the variational formulation of the problem, it's easy to understand what we have to do, okay? Here is the original problem, and we have this concentrated integrals for the problem. So we have to be able to pass the limit in these terms. So we have to understand how this kind of integrals, we have to describe how these different concentrated integrals converge to surface integrals. That is the case in the boundary condition, okay? So what we have to do here, we have to be able to pass the limit here, and we have to show that this limit problem is actually the limit problem of this equation. And we have to show in which space it's possible at all. So this problem was introduced by Arrieta, Jimenez Casas, and Rodrigues Bernal, and they have studied the problem, the elliptic problem for the Haubrink boundary conditions. And they have just considered the case without oscillation. The G epsilon, of course, it's not dependent of epsilon, it's a fixed function. And in this work, they have studied those integrals here, the concentrated integrals that they call. So after that work, they have considered the problem, but just the problem, no, a parabolic problem, but they have just studied the upper semi-continuity of the attractor. And they have done this in those two works, and without oscillation. So we thought to understand if the oscillation here can affect the problem in a different way. And we try to do this. And we first consider a nonlinear problem in a square to understand how the oscillation could affect the limit problem. And we saw that in the end, we appeared this term at the nonlinear boundary condition in the limit problem. So after this work, we tried to consider the problem of the parabolic problem, and we tried to consider the case of the lower semi-continuity of the attractor too. So, it's the goal of this work here. We have extended the results of Casas-Bernal to parabolic problem, okay? In the OR neighborhood now presents a highly oscillatory behavior, and assuming hyperbolicity of the equilibriums for the limit problem, we could obtain the lower semi-continuity of the attractors too. Okay, this hypothesis here about the hyperbolicity of the equilibria, it's not so restrictive condition since it's a generic property, and it was proved by Henry in his book 7 years ago. Okay? So, we have obtained this result too using some abstract results from this work. And how we can do it? We have just, to get the upper semi-continuity of the attractor, we just have to understand how the linear operators of the original problem behave, how the linear operators, we have to understand the behavior of the linear operators with respect to epsilon, and we have to study the nonlinearity with respect to epsilon too. And then we have to prove that nonlinearities are continuous with respect to the parameter and their derivative too. And I will show which kind of estimate we have to get to the linear operators in the next slide. So with these two conditions, we can show the upper semi-continuity of the attractor just using abstract results. If we assume or working in a gradient system and supposing the hyperbolicity of the equilibriums, we can get the lower semi-continuity of the attractor, because since the system is gradient, the attractor is just the union of the unstable manifold of the equilibriums. If the equilibriums are continuous with respect to epsilon, we can show that these unstable manifolds are continuous too with respect to the epsilon, and so we can get the continuity of the attractors, okay? It's the idea that you use always, that we are trying to understand how the attractor are working. Okay. So here we have the operators. They are given by this bilinear form. Okay, it's pretty easy. Here we have a term that we have to be careful about it. We can define the linear operators by these bilinear forms. They are very nice, self-adjoint, sectorial operators. We can show that there exists a constant that we can take bigger values to get this property. They are invertible and nice. So we define the nonlinearities too. They are given by this integral function, this functional. And so we can just write the original problem like in this abstract way here. It's known that this parabolic problem are well posed in H1 for each epsilon, and there exists a global attractor for each epsilon, and they are uniformly bounded, okay? So we have just to prove the continuity of them. Okay, so to prove, we have to estimate the operator, and we have to prove this kind of estimative. And it's possible because we have that these linear operators given by the concentrated integrals converge in a in the norm by the linear operators in those space here, okay? So using that estimate, we can show the convergence of the linear semigroup, like here, and we also can show the convergence of the Hertz-Lorentz operator, so we have the convergence of the spectrum of this operator, eigenfunctions, eigenvalues, and this kind of perturbation was deeply studied by Kaplan in this book, Perturbation Theory of Linear Operators. It's a kind of perturbation very known in the literature. So, after that, we have to study the nonlinearities, and we can show that those properties for them. They are uniformly bounded in epsilon, Lipsch, globally Lipsch in epsilon 2, and we can take the convergence with respect to epsilon in bounded sets in H1, and we can prove the same properties for the derivatives. So using this, we can show that the upper semi-continuous of the attractors. We have these three properties for them. They are uniformly bounded. The attractor A0 attracts the union of the A epsilon attractors for epsilon 0 is small enough. We have the continuity of the semigroup 2, nonlinear one, the nonlinear semigroup, and we have the estimative infinite time, and we have the upper semi-continuity of the attractors, okay? So with the upper semi-continuity of the attractor, we have the upper semi-continuity of the equilibriums too. So now, if you suppose the hyperbolicity of the equilibriums, we can show that they are continuous with respect to epsilon, because the F is continuous with respect to epsilon. So using a kind of function, implicit function theorem, we can show the continuity of the equilibrium. And we can, since the problem is gradient, we can show that the unstable manifolds are continuous with respect to epsilon 2 in H1. So we can get the continuity of the family of attractors. So it's the scheme, okay? So let me, since we have the abstract results proved here, this problem is pretty simple. Okay, it's not so pretty simple because the problem here is to get to understand how the nonlinearities behave with respect to epsilon. It's the hard work at the article in the end, okay? After using this result, it's almost just to check the hypothesis, and we can get the continuity of the attractor, okay? So it's all. Thank you very much.